This video is for topic 47b, normal distribution, standard problems, and z-score. So the whole point of this is we want to find a percent probability area that does not fall directly on a standard deviation value like we were doing before. We are kind of stuck in terms of figuring out the different values. However, we can go ahead and utilize Desmos graphing utility to help us find those. And the tool that we are going to use is the normal dist, where we type in the mean, standard deviation, and then go ahead and use our zoom fit and then min and max manipulations to go ahead and manipulate this bell curve that we see happening there. So let's go ahead and take a look at an example. So let's consider a time required for a college to complete a standardized math exam. Suppose for the population of students at a particular university, we see that it's normally distributed, which is very, very key. We also see that the mean is 53 and a standard deviation of 10 minutes. Okay, so for part A, find the population of students who take between 35 and 55 minutes to complete the math exam. So like all problems, we're going to go ahead and put our mean on and then go ahead and walk out our standard deviations to give us this particular bell curve, this normal distribution. And we want to find between 35, which shows up right here, and 55, which is right about there. And as you note, looking at this area, it falls not on the standard deviations, and we need to go ahead and use technology because of our old empirical rule does not work. So our steps: normal distribution, we type in the mean and standard deviation. We click zoom fit to take us. We click find cumulative probability, and we want to find between 35 and 55. Notice it gives us a decimal. If I wanted to go ahead and turn this into a percentage, we multiply it by 100, giving us an answer of 0.54 or 54% of the students falling in that category. Going ahead and taking a look at B, C, and D, now that we know how to utilize this technology, why don't you go ahead and try B, where we're trying to find the amount less than 42 minutes. C, we're trying to find how many students expect to finish, how many students would finish the test in 60 minutes. And if 60 minutes is allowed for the exam, what is the probability that students would not finish the exam in time? I'll give you a moment or two to go ahead and try those out. I'll reveal the answer in 3, 2, 1. In B, we get an answer of 0.14 or 14% since we're less than 42. We also see that plugging that in, we're going to go from negative infinity to 42, gives us our decimal. Notice we rounded up in this particular case. In part C, we're looking for less than 60 minutes or less, so that gives us 0.76 or 76%. But here again, I wanted to know how many students, so we need to go ahead and take the number of students, 870, and multiply that by our percentage, giving us 660 students, which we see, here's my percentage, multiply it out, and we get 660 students going through there. In part D, we're looking for students who are not able to finish the exam. Not being able to finish the exam is anything higher than 60. So 60 to infinity, we get 0.24 or 24%, which we note here. Again, we go 60 is the min, infinity is the max, and multiply by 100 to get the percentage, or given as the decimal. So utilizing technology, specifically normal distribution with the mean and standard deviation, and manipulating the mins and maxes, we're able to go ahead and calculate these percentages that fall not on our standard deviation values. Now, moving on, since there is technically an infinite number of means and standard deviations we can have, we would technically have to do this an infinite number of times. Well, mathematicians figured out a shortcut, and basically what they said is, well, we're going to go ahead and standardize every type of mean and standard deviation that we find. And if we do that, we can put all of the percentages onto just one single table and one single bell curve. So what they did is they came up with something called a z-score or a z-table. So notice in this graph, notice in this picture, we have the same percentage breakdown, but instead of the standard deviations, we're just going to use a value of 0 for the mean, and just the standard deviations are going to be single integer values of 1, 2, 3, or -1, -2, and -3. So we're simplifying it down so that way it's standard across. Also what that does is that gives us a table of values where we can go ahead and confidently predict and know the area for various numbers of z-scores that fall. So if I were to go ahead and look at this table, and I wanted to know the area below, let's say, z is equal to negative 0.63. We would be able to go ahead and go on to our table here. It's kind of blurry, but we could see negative 0.6, and we could find the column of 0.3 at that point and kind of come down. We would be able to know our exact value. Right? This is one way to go ahead and calculate the percentages below certain values. We have this table that we could use. Luckily for us, Desmos allows us to go ahead and do that calculation. We don't necessarily need the table, but it is in fact there for us and is a way to standardize all of the values. Okay. So how do we make a z-score? Well, creating a z-score is actually quite simple. All we have to do is this calculation. Z is equal to x minus the mean over standard deviation. So the data point in question is equal to the data minus mean over standard deviation. So let's go ahead and take a look at this example. So on a math exam, scores are normally distributed, which is great. Key part of this. We have a mean of 200, so that means I'm going to plug in 200 for that value. We have a standard deviation of 40, which is going to go there. And the question in value, the value in question here is we want to find a z-score for an exam of 90. So 90 is going to go into that blue spot, which gives us a z-score of negative 2.75. Why don't you take a moment and see if you can go ahead and figure out example F, history exam, the mean, standard deviation, and scores are given. I'll reveal the answer in 3, 2, 1. We get an answer of z-score of 2.7. Brilliant. Now, the real power of doing z-scores is it allows us to go ahead and take data, right, and that come from two different sources and actually compare them. So in this particular case, we have two scenarios. We have Abby, who took a math test on the SAT, and Betty, who took a math test on the ACT. Well, they're two different tests, two different types of scores. How do I know who did better? Well, you would think, well, the bigger number, but again, they're two different scoring systems. How do we go about doing that? Well, if I turn them all into a z-score, I can go ahead and graph both of those on the same bell curve and figure out who scored higher, higher being a higher z-score. If I wanted to figure out for some reasons who had a lower value, we'd look at the lower z-score. So being able to take and compare to how well you did on two different exams, two different things, is very, very powerful. Just like here, we could go ahead and compare the results of this math exam to this history exam and see how well they did. So let's go ahead and do this with our SAT, ACT. We're going to assume that they're both they're both stated that they're normally distributed, which is excellent. We see that we have the means in both of these. We see that we're given the standard deviations. We're also given a value in question that we want to go ahead and turn into a z-score. So doing our calculations, we get Abby's z-score to be 1.8 and Betty's z-score to be 1.5. We therefore can say that Abby performed better because on the standardized data, her z-score was higher or larger as we're going through. So again, being able to go ahead and compare two different sets of data with two very different means, two very different standard deviations, two very different populations, two very different scores, put them on the same graph, we can go see who is doing better, who's doing worse, etc., etc.